All right. Welcome to the stream. How's it going? Hope you're well. I'm Agent Ultra, and on this stream we do some recreational programming and we just build things and learn about stuff. And for the past little while, I've been working on a little project. We've been working on a little project to figure out how to build a multi-user dungeon, a MUD server in Haskell. What is a MUD server? It is the precursor to massively multiplayer online games. They are text-based, but they feature multiple players playing at the same time concurrently in somewhat real time. And yeah, that's how you do it. You used to connect to them in like with telnet clients and multiplexing telnet clients and all kinds of stuff back in the day. It was like the premier way to play online games back in the day. And we're just we're doing it in Haskell to learn a little bit about software transactional memory, networking. I'm also embedding Lua in it, so you script the game itself in Lua, and so learning how to embed Lua scripting into Haskell applications and things like that. So it's been pretty fun, gotta say, and we've come a long way. Tonight, we're going to work on, well, we're just getting to the point where, like, we've been able to implement a look command. And we've been working on trying to get the player to be able to move from one room in the map to another. Be able to implement that. Last week, I did a little bit of cleanup on some of the codes. We have, because it's multi-threaded, Haskell's by default is green threads. When you fork a thread, you call it like fork IO or whatever. They just run, and if they crash, they crash. They don't throw the exception back to the main thread. So we fixed that because the server is not really operable without all of its threads running. So we added tracebacks. So if Lua crashes, like there's an error in the user code that you can check, we'll be able to check the logs of the server and find out what happened there with the code. And yeah, I don't know if we should maybe get back into the movement, or I was thinking of just hacking out and prototyping out and understanding entity component systems. So we kind of want to build the way the objects in the game, the entities in the game are represented, build a framework for that. I thought maybe we would do it with an entity component system for it. So I don't have one in it yet. We kind of had like the makings of something in it. Under a simulation like component. But I'm thinking maybe of just like prototyping out, fleshing it out, seeing what we can learn there, what we can do there. For some reason, Emacs is locking up. There we go. So, what do we have so far in terms of our ECS system, our entity component system, is just components, I think. We have a definition of a component. The component values, and we have a component type, which is a map of text to value. The values that we support right now are, looks like ints, floats, and text strings. Probably should have some more data types in there, maybe, but that might be enough. So the definition is something that that's written in, will be written by the user, probably in Lua. And it just sets the schema up, basically. The entity component, let's get into entity component systems. Like, let's talk about this a bit. An entity component system It's just a way of structuring a program's data. You have a lot of live objects that get a lot of small updates because they're being updated by various systems in your program, like physics and I don't know, other forms of game logic. Right, so you got like physics, you got like rules, you've got all these sorts of things. The one way a lot of programs structure things is they like to combine data together with behavior, the so-called like object-oriented programming sort of style. Or even in C programs, before you even get into OOP, you might pack things together in structs. So a struct with like game entity. Right, and it might have a position X, position Y, might have, I don't know, health, and all this other data, right? And then in your game scene, right, you might have a bunch of these game entities all existing at once, right? You've got enemies, you've got your player character, you've got little bullets and objects and things flying around. So what do you get? You get a big array, right, of game entities. Maybe, I don't know, like 100, something like that. I don't know. Sorry. Right? An array of them. And you process them all at once, one after the other. All fine and dandy, like not the worst way to structure things, right? I mean, your struct is going to get pretty fat if you structure it this way. It's going to be pretty big. And there might be a lot of padding in there depending on, the other kinds of data in there, because maybe you have other structs of something else, I don't know. And those are going to have padding in it, and it's going to take up a fair amount of data. And they're always going to be kind of updating little bits of it. So you're going to like randomly access bits into this array to update those various entities in the scene, depending on your game logic. Okay, your game logic is going to have to run through this whole array, updating all the relevant entities over and over again in various passes. Right, so there's a couple of reasons why this is like not the best way to structure things. There isn't like a best way. Well, the best way is really like whatever works for your game, but performance-wise, we can do a little bit better here if we structure things a little bit differently. So what an ECS asks us to do, right, is separate out the entities from their data. Right, so instead of like one index in that array of entities being one particular object, we're going to update like the player, for example. Right, we just turn those into IDs. We make those a first-class thing, and then we create components. Right, that have other elements to it. So we might have like a health component. Right, it has a bunch of stuff in it. We could have another one like a physics component or position component. All right, let's take on our example here. And that would have all of our position data in it. All right. So instead of like having a big, fat, or huge array of game entities, right, we have arrays of the components. And the idea being like we get a lot of more component. We get a lot more data locality. All right, So although if we ever have a function that needs to just update the positions, doesn't care about anything else, you know, we don't have to go through these this whole array of big, huge game entities. We go over a whole array of just the positions. Smaller amount of data put together might be a little bit better. We might not have entities, like 100 entities that have 100 position components. Like we might have fewer position components. Because we might have entities that, you know, don't have position components necessarily. So that's another thing, is like we only have to iterate over as many entities that have live position components as there are, right? So smaller amount, better data locality, because it's just the position data together when we're operating on business logic that just touches positions. That sort of thing. Right? And the third thing, so that's entities, that's components. And then the third thing in the entity component system is the system part. That's where you write all of your game logic or your business logic or whatever. That just looks for what it needs to do. So you might have a physics system, right? And the physics system just needs to touch positions and velocities. So it might look for all the entities in the system that have, system is getting overloaded, all the live entities that are in memory at the moment that are live that have velocity and position components, and just update those, right, with the business logic. It doesn't have to touch all of the entities, just those. So we're going to try and figure this out see if we can do something like this in Haskell. That's kind of what I want to try and figure out, how to do this in Haskell. So component, we kind of have a type for. Now we're kind of making component just a bag of labels and values. This might be an okay enough structure. Components are just data, or should be just data, right? Just position data or what have you. So a valid value of this component, right, type, let's make one. It'd be the empty one. That wouldn't be a very useful one. But let me actually add, say, import maps. And let's create one. We'll go from list. Yeah, we can do like, we can implement our position component, a value of our position component, right? Let's say X. Let's make it be num 2.2. All right, and we can do Y with vnum 2.3. Not in scope because, well, let's bring it in. I gotta set overloaded strings. That should do it. There we go. So what I don't like about this right now in this code is that it just says component. Right, we don't know anything else about it. About it. And yeah, I don't know. A good type for me sounds like, I think would probably be, I think I know what I was getting at here with this code, but Thinking maybe I want to change this here though. I kind of want to be able to be like a position component, right? Right, and it'd have my definition of it. Almost like a record. And I want like my X to be in, say, a double here. My Y to be a double. And I think maybe the better way to do this, the nicer way to do this would be to make a type class for components. Now what methods would be in it? All right, and this is where we need, so what do we need to think. Now, I don't usually like to reuse type classes unless there's properties associated with them. But this might be a useful case for them to bend that a little bit. And who knows, maybe we'll discover some. But we need to think about like the methods that we would use on a component in order to get its data. We'd have to probably get the data out of it. Which could just be off the accessors and things like that. What else would there be? I'm kind of not coming up short. I think this is like a little... I don't know if there needs to be anything... I just want to know that it's a component. But I don't know what methods it would have. Maybe we don't need one. So we could also cure the problem I have with this by making sure it has some kind of value in it that tells us what type of component we have. And I think this is going to get a little bit important later on because I mentioned it's systems, right? When we're talking about a system's going to want to update, say a physics system is going to want to update entities that have position and velocity components. All right, so we're going to have to get out all those components out of our system, out of our data or whatever, right? Just the ones that are of those particular types in order to update them. So we could also change its component to have some kind of label value that tells us that type that we can compare on. All right, we can make this, say, the component data. And we can have a component label for kind or type. Like this. And now we would be able to at least query for those names. Since they're all going to be text, like we're just going to have to trust the equality value of text for that. And if you type things in wrong, that's fine. And that's going to be your problem. You're not going to get what you expect. But we won't be able to like do any type checking or anything like that, I guess. That's what I'm saying. Unless we write it ourselves. And given that like the user is going to be writing the stuff, the definitions of these components in Lua and the systems in Lua, they're not really going to have the Haskell types anyway, so it might be fine. This might be fine. But we're definitely probably going to need that type there, I think. That's not going to be a new type anymore. Yes, that's going to be a data. And then we're going to have a bunch of type errors because I've changed the definition of this thing in this module. So, yeah, let's add this in. Okay, so our definition is going to need a name field as well, so we're going to change that. Yeah, we'll take that. Call it the schema. All right, so we need to add that field. So this is our parser. Text definition. It returns a pair. Well, we do get something the code calls a label here. Right, okay. So we can change this to definition instead of a pair. And that should work there. Got an error message to-dos there. Good times. Sorry, chat. Let me make sure that I've got you up and out. I'm just double checking, seeing how things are going. If you're following along and you're not like super into Haskell or whatever, maybe you're just new, curious, just like muds, whatever the case may be, it doesn't matter. Feel free to like stop and ask questions. I don't mind taking diversions. A little backseat programming is good now and again. Fun times. Okay, so that solves that problem. Now get fields works there just fine. Okay, so that should be good there. Let me just get GHCID running here. Right, on 44. So the instantiation here. So the definition has the component name or the component type. Or we're calling it definition type, yeah. So component type. Component type is the name of the field as well. And component. I just can't call it type. Call it type with an underscore. That's fine. Type's a keyword. So we get our instantiated values by mapping over the component values. and the definition values. Or we look up in the definition for each key in the component values. And then we try a type check, a really basic one. And if it does match, then we return the value. So map traverse with key is going to change component values map based on the definitions, essentially. And so we create a component there. And we also added the field there, so that's all we got to pass through. And that should type check again, and we're good to go. So now we can instantiate again. Okay. Entity, pretty simple. Let's create a little module for that. Nothing really to it. An entity is just an identifier. That's it. We can make our identifiers anything we want. We can make them integers if we want. We can be specific and make those 64-bit integers. Okay, so we kind of got maybe two things we have here. So now, if I reload this, our component can be, what is this, like position? And there we go. And now we know it's a position component. And here's its component data. And that should be translatable, pretty translatable to Lua, I think. We'll have to encode this as a table, and then a table for the component itself with its component type position. So that's all going to be pretty easy to marshal over there, back and forth as we need. Okay, so that's components. We've got entities. Next is, I guess, systems. Now, here's going to be the tricky thing. How are we going to write... Well, the systems are going to be written in Lua. Right, that's ultimately what we're going to be doing, is like all your game programming, right? It's going to be in Lua. The game program is going to be writing the systems. So any of your game logic is going to be written there. And we have to have a way for you to tell the server what systems you... We have a way of telling you what components there are, but we have to have a way of writing those systems out, right? And either the server has to know about the systems, or we have to just call endpoints, or call some Lua code to update systems. Now, I think it's probably more likely that we'll have... The API for this should be that we would like register a system. Maybe have like a startup function that the Haskell server calls to get those. So the game developer can then call a special function to register their systems. Because a system has to be able to say a physics system, has to be able to say which components it's interested in processing and being called on. Yeah? So let's sketch out some rough Lua code that would look, just prototype, just not even fully functional Lua code that would do this, right? Just to get an idea of what we might need. All right, so let's call it physics system, since that's our running example. Right. Right there. Arguments. Does it take any? Maybe. Maybe it operates on one set of its registered components, right, at a time. So it would take a position component and a velocity component, say. All right, so these would be components that I could get in. And then I guess the idea would be that m.physics would update these, mutate these. But how would the Haskell side know about that, those mutations? Right, it would be nice to be able to write position plus x plus equals like 0.0 or like velocity dot x. I don't know. Position dot y plus equals velocity dot y. Something like that. That would be super nice and sweet. But on the Haskell side, when this function gets executed, right? Like it's not going to leave anything on the stack for us to look at, to be able to go, oh yeah. Or will it? I think Lua consumes the arguments off the stack when it calls the function. Pcall. So pcall behaves exactly like call. Maybe call is the one that tells. So right, to call a function, you got to do the first. The function has to be called is pushed onto the stack. Then the arguments are pushed in direct order. Finally, you call. And args is the number of arguments that you pushed on. All arguments on the function value are popped from the stack when the function is called. Okay, so they're removed from the stack. The function results are pushed onto the stack when the function returns. The number of results is adjusted to end results, unless end results is multi-ret, multiple return values. In this case, all results from the function are pushed. Lua takes care of the returned value, that the returned values fit into the stack space. The function results are pushed onto the stack in direct order. So that after the call, the last result is on top of the stack. Right. So going back to our example, that just means that when we call this on the Haskell side, we're going to be pushing the position component, the velocity component, say as we're like traversing over the queried set of things and calling the physics system on them. Right, traversing over the set of position and velocity components, and then calling this function on each one. But it's going to pop those off the stack. So we have no way of really knowing that this mutation occurred once control returns back to Haskell again. Unless we return, right, velocity, like using, and then we'd have to get into the multi-ret stuff. Right. Or we could have an API function What would it be like, set component? But we'd have to know which component. So I don't know if this API would really work either, right? Because we don't have component IDs. And I don't think I'd be able to... Plus, let's say velocity.x. Right. Maybe on the Haskell side, we could get this function. It gets a component. Yeah, but it doesn't know. We'd have to give it maybe the entity ID. That would tie it back, and that could work. Right, and so this basically gets the position object back again, the component. The field and the value we want for that field, and mutates it in the memory of the server. Right, that would be enough to do that. Although we don't need the whole object, we could just have the component name. Or probably like that. And that way the server would know about it. So we can do position type y, and then the value we want to give it. All right, so this would kind of, as we're traversing and running this system, right, over all of the collection of position and velocity components, we would have to do another set component, would do a lookup into the position components for this entity ID and do that as well. So it's just one extra lookup. Yeah. It would be super cool if we could have like the reference. Like I really kind of like the idea of running, just mutating the objects. That was super nice. Looks nice. But maybe this could be the better way of doing it. If you return each of them, we could presumably, if I can figure out how multi-rep works, get those values out. And then on the Haskell side, at least in the traversal, we know the entity ID we are on, hopefully. And so we would we'd update each of these, we'd put these components basically in the data, in the memory for that entity ID, modified such as they are by this Lua code. Okay, let's investigate multi-ret and see how that works. Multi-ret, okay. Option for multiple returns in pcall, right? So we have to give... Multi-ret is a num results value. And we have to give num results as the argument to pcall. So we could call this saying we're expecting 2 values, I guess, back. Is that what it is? Or a multi-ret? We're expecting multiple, I guess, values is what it's saying. It doesn't really say how many, though. So in this case, when it is multi-ret, I guess end results, the num-args, or num results argument there. In this case, all results from the function are pushed. Lua takes care that the return values fit into the stack space. Okay. And the function results are pushed onto the stack in direct order. Okay. So we would have to, we wouldn't be able to know. Well, we could figure it out, I guess. As long as the user doesn't mess, the programmer, the game programmer, doesn't mess up the type arguments. Like, they don't say, like, write something like this. Right. They don't change the type field. Right. Maybe we can make this into a convention, something like this, so you don't modify it. You know not to modify it. But as long as they don't do that, they could just return that. The convention for writing your systems then would just be like return all of your arguments. Mutate your arguments and then return them. Right. And then that should work nicely, because then we just pop those off the stack and do all the stuff we need to do while we're traversing and executing these systems on the Haskell side. Then well, the last part of this is registration. Okay, so let's get rid of this example. Let's just stick with this one. Okay, so we'd have to have some kind of startup function on startup, maybe, where you can register a system. You would give it a name. You'd have to tell us which component types you're interested in. So say position and velocity. In fact, this name might even want to match that name. And that might be enough information from the API for us to implement the functions. On the Haskell side, we're going to need to know the number of arguments to the system and how many arguments, and that it's going to return the same number of arguments returned for multi-ret purposes. So we'll have to store that on the Haskell side, but I think we should be able to implement this as well. And that would be our system for physics, and then like we could register a system for health. All right. Or maybe damage. We're interested in the health component and the damage component. Now, damage is an interesting one because that involves two different entities. So far, I've been thinking about this in terms of like one entity just being updated by game logic like physics. But we also need to handle that case too, because like our users are going to be, you know, playing a game where they're going to be attacking mobs, maybe each other. Which the reason why I'm working on the entity component system is because I want to like be able to implement the player as a mob, as if it was just any other entity, like a mob, so that you could implement that. So if we're registering a system, we need not only to know what components to query for, but we also need to be able to specify that the system, something else about the system. Or no, maybe I'm thinking about an ACS wrong in the way you would design it. Yeah, because like I got two things attacking each other, right? And they want to, one entity wants to apply damage to another entity. So in order to do that, all right, we need to change some data somewhere. I need to be able to tell the other entity that you've taken some damage. And then the system needs to take that information and update the health component. So this would be like an apply damage. That one's pretty easy. But we can imagine, say, the health amount. Might have some business logic checking the amount into zone over 0. Right, if and damage amount is less than or equal to health dot amount. All right, we write something like this, where the health dot amount then is decremented by the damage amount. All right, else it means we can do the health dot amount. So it's got to be greater than that, so just equals 0. And then maybe that signifies the character or the entity is dead or can't play anymore or whatever it is. However you want to interpret it. So how do I do damage to something? So I basically need to have a way of writing a system that can change some values to a component that belongs to a different entity. How would I register that system? All right, let's say I'm interested in the damage component. But maybe there's like an optional third parameter here. Or we can put like an entity ID. We wouldn't be able to write out the entity ID ahead of time. We just want to be able to specify that it takes an entity ID. Right. Maybe. It's like a weapon component and a damage component, right? And maybe the missing piece here is being able to invoke a system from Lua here. Maybe that's what we're missing. So we get like implement an attack command, for example. Let's implement a pseudo attack command. All right. Presumably it would be like, I don't know, a name that you would type in, like attack the foo, and then some name of an entity you see in the room with you. And then we'd have some API for looking up entities in the current room and getting their entity ID, something like that. Look up in room. You know, tokens, whatever, 2. All right, and if we have an entity ID, all right, then we can do something else, like do the attack. So maybe we want to invoke system. And that would be the attack system. And then we can give more arguments. Would this work? This might work, maybe. Like the entity ID we're trying to attack. All right, and what would that hypothetically look like? Attack. All right, it's going to have the systems. All right, so the weapon, or the components first. The weapon and the damage component. All right, maybe the entity ID. Now this would be not. So how would we connect up the two functions here, the system here? We call invoke system, right? We register attack or do damage, sorry. A weapon and damage component. So what does invoke system mean? What does it do? Right? I think what this means to me, I think this would make sense. So we are invoking the do damage system, but we're going to look up the components from this particular ID when we invoke it. But that's not quite right, because when we're doing this hypothetical scenario, we're doing the attack, we want to, you know, take some data from entity 1 and do it to entity 2 so they can interact, right? So we're going to need 2 entities, IDs. All right, so we're going to need the connection ID's entity ID. Target entity ID. And then we're going to need a source entity ID. And imagine we have some function for getting that off of the connection. Maybe it's player entity. So we have the source entity ID, the target entity ID. And now invoke system on has enough information that, well, at least we know the source and the target, but we still don't know, and we still don't have enough information based on register system. Like do damage just says these components, please, but it doesn't say from where. We meant to say weapon from the source entity ID and damage from the target. All right, so that one's going to be, it's not quite there yet. How would you do this in an ECS kind of style? I'm thinking we're starting to run a little bit off the path here with this design. Because I'm going to have to specify if I'm... Like, this is a very specific scenario we're working through. And I'm pretty sure that we could think of other scenarios as game designers that we would want to be able to do. And I'm going to have to implement a special case for each of those in this system, which doesn't seem right. Like, what if I want to have an attack on multiple entities at once? And apply damage to all of them. Right, so like some kind of area of effect spell, or, you know, something like this. Maybe some kind of environmental effect if I'm running a weather system for my game. So I think I need something a little bit more general, and not so specific to each particular scenario. So can we implement this, say, attack system without mentioning in the logic of our ECS, entity components of systems, you know, the structure of this particular behavior, this particular system? Can we do it with just components? All right. That's what we need to make sure we know. Yeah. Yeah, maybe you can. Maybe you have an attack component. You'd have to think about this in terms of components. So you have an attack component, you have a health component. Right? The attack component may have a field like right, an entity ID, so maybe like entity ID 23, like 2. From and an amount of damage to do. Right, so we have a system that processes do damage, right? It's looking for these attack components, and it's looking for an entity that has an attack component and a health component. Right? And maybe a health component has just like an amount. So we might also get the entity ID as the first argument. Because if we're writing a system that processes just the components attached to the entity, this attack could be, we could compare the 2 value here in this component to the entity ID we have ourselves and apply the amount and do the business logic to apply the amount of damage and reduce the health amount in this health component on this entity. Right, and then we might also write another system that could, like, react to this in terms of a component by also processing the attack and various other components and apply it to those things. That might be the way to do it. Okay, so let's start doing this. So yeah, we'll have systems take implicitly an entity ID as the first argument, and then the requested components associated to that entity ID from the register call. Yeah. You modify your arguments components, and then you return them. And then the Haskell side of things will make sure to update those and apply them to change the state of the components in the system. And then onward we go. And this will be how we'll end up implementing a lot of the logic even for the simulation and those sorts of things. So there'll probably be some API for telling the simulation about like passive systems that update on every tick, and systems that react to things and that sort of stuff. But I think this might be good enough for now. So let's hop back over to the Haskell side of things. Component. We added the entity module. Let's take that change. Definition to component. Also adds definition type. This is used to uniquely identify. Of the component for systems to query. /use. That's good. Okay. And then add the entity file there. We have to update the Cabal file. Add that module. Then we need to store our entities somewhere. So let's go to the state. We'll add entities. Let's change the type. Okay, so our entities are just our entity IDs that are live. I'm just thinking, like, what structure should we store them in? I guess a vector. Concurrent collections. I want to see if concurrent collections has a vector. STM containers, that's the one. A map, a bimap, a set. That might be good enough. We had O1 lookup. Inserts are amortized. That would be good. Because, are we going to be concurrently manipulating entities and their components in STM transactions? Do we need to wrap them in STM transactions? Potentially. I think we might, because the simulation is going to want to maybe passively update an entity at the same time that a command, which is run and executed in a different thread from the simulation, is also going to want to do the entity. Now, we do order these things internally so that they get processed according to the server ticks in the order in which they happen. So I don't actually think we'll have concurrent updates of this. So we might not actually need that. We could probably just put it in a straight vector of entity IDs. Now, I might be shooting myself in the foot here at this design, potentially. connections come in and out, right? And the server is also going to be processing things, processing the events in the simulation, for example, and its inputs. And changing the vector to remove an entity, for example, when a disconnect happens, would be a thing we'd have to handle somehow. In the case where like it disappears, like we do the update and then it disconnects, and that's probably fine. But if we we disconnect and then we do the update, probably fine. But maybe not, because maybe we want to be able to say like, okay, like this entity is no longer here, we should not process this event anymore. Or we should. Design decisions. The consequence of putting an STM container set, and we don't end up using that, is that refactoring that later on and reversing that decision, we'd have to switch out the data structure and potentially, yeah, we just have to switch out the data structure and like all the methods that use. Hopefully the APIs aren't too different if we change our mind later from set, the functions we use on set and the functions in like vector or something like that. Or just like a straight regular non-STM set. We don't want the STM overhead. Yeah, which isn't a lot, but it's present. So why don't we do that then? We'll do an set. We need entity ID. Down here, we need to do the update. State entities. And we can do new IO. Pop those in there. Okay, so now we have our entity IDs, and what next? The components associated with those entities. We're going to need a map for that. And server state entity components. Right, and this is where we connect those things together, so it's just a map. Entity ID. All right, and now what are we gonna? We're gonna store the entity IDs. No, I'm not gonna store it like this. Excuse me, something's going on with my eye here. The entities. We don't want to store them necessarily together in a map with the entity ID, do we? We want to process all the components together. Right, so the whole point of an ECS system is that we keep all of our data contiguous together, which in Haskell, not super important. So, because everything's allocated on the heap anyway, but hopefully we can get some kind of locality there. So, entity ID, not quite it. Not quite it. I almost want to have component types and the the live components that they're together with. Like, let's draw this out a little bit. Meow. Meow. All right, so this top one here might be position. Oh, my O is amazing. It's really hard to draw letters with a mouse, to be honest. And the bottom one might be velocity. And these should just be straight arrays of components, right? X, Y, X, Y, X, Y, X, Y, X, Y. Right, all the way through. So I guess maybe one part of the component, or all components, might be the entity ID it's associated to. Right, the entity that owns it. The entities are going to be like way over here. And so this system here then, right? The position might be like an index 0 of the position components, but the velocity for this entity might be in like, I don't know, index 4 or something. All right, so the systems process just the components. They don't really know about individual entities. Only insofar as they know them as like opaque identifiers. But it doesn't really mean anything to the system a whole lot. All right, as a component should just be processing like a physics component should just be processing right? A pair of these. By entity, isn't it, though? Let's do a little research. Let's get a simple entity component system. Oh, gosh, excuse me. Okay, as promised, the entity is very simple, yeah. Component. So we have like a struct or a record. Pretty simple. Okay, they do use unique IDs for the components. Okay. In this system, anyway. Okay. The signature. Okay, so since an entity is simply an ID, we need a way to track which components an entity has. That's what we're working on right now. And also need a way to track which components the system cares about. Okay, cool. So this person shows a very simple approach of using a bit set called a signature. Each component has a unique ID, which is used to represent a bit in the signature. Okay, so just using a set, essentially. A set of unique IDs for those components. Okay, so you know which components an entity has. Okay, that makes sense. The system would also register its interest in certain components as another signature. Then it's a simple bitwise comparison to ensure an entity's signature contains the system's signature. An entity might have more components the system requires, which is fine as long as it has all of the components the system requires. Okay. Then they have something called an entity manager, which is in charge of distributing entity IDs and keeping record of which IDs are in use and which are not. Yeah, that's kind of what we're using in our server state. Okay, so like a set, essentially. And the component array. So we need to create a data structure that's essentially a simple array, but it's always packed array, meaning it has no holes. If an entity is just an index into an array of components, then it's simple to grab the relevant component for an entity. But what happens when an entity is destroyed? That index in the array is no longer valid. Remember, the entire point of use is to keep the data packed, meaning that you should be able to iterate over the all instances array without needing to sort any if valid checks. When an entity is destroyed, the component data it had still exists in the arrays. If a system were to then try to iterate over the array, it would encounter stale data with no entity attached. For this reason, we need to keep the array packed with valid data at all times. So they solve this problem by keeping a mapping from entity IDs to array indices. When accessing the array, you use the entity ID to look up the actual array index. Then when an entity is destroyed, you take the last valid element in the array and move it into the deleted entity's spot and update the map so the entity ID now points to the correct position. There's also a map from the array index to an entity ID, so that we're moving. Yes, this is all well and good. Okay, so the position, the point we're doing here is we're trying to create that mapping from entity ID to the components it has. I think the idea of using a component ID might be just the trick. Right now we have types, as text. Not super great. Might be useful for registering though, because I like that API still. Right, you wouldn't want the game developer to have to remember all the like numbers that represent these things here, but I can remember a string, a thing I called it. Yeah, but it's not going to be terribly efficient for our map to it doesn't have to be super efficient necessarily in this case. It is just a mud. But in the state, right, make this say entity ID to a set of component IDs or like text. Yeah. So instead of let's make a type for that. New type. Mm-hmm. And we could just make a text here for now. Right. And then if we change our mind later, we have no big reference. Like, constructor will hide everything. It'll be just fine. Just fine. We could... they call it component. We're calling it type. Let's keep it. Let's just keep it as type. We'll just fix this here. By adding the constructor in the parser. And here. Component type. There. And then on 68. Oh, sorry, its definition doesn't have component type, just labeled. Right. Right. So then data. Oh, as an unordered containers, which we don't have as a dependency yet. We can add that. That's not a problem. Oh, it's a parser. Oops. Okay. Maybe it's dash. What's in containers? Oh, map.set, data.set. Oh, gosh. Okay, cool. And 80. There we go. So we got to initialize sort of state entity components. And put a hole there. Import qualified. I'll jump back over there. Actually, we could probably just put empty, can't we? No, it's an SMAP. Sorry. To do SMAP. We don't even need that. New IO. There we go. Super duper. Okay, so now we have a way of mapping the entity. We have the entity IDs, the set of entity IDs that are currently like alive in the system, and the components that that entity owns. All right, or is part of that entity. Then we need all of our component data smooshed together for all the things. This is going to get tricky. Well, let's create a committee commit for what we have so far. Okay, we just added the map and component type. Oh, right. So this is not quite right. We wanted the map to be not set of text, but set of component type. And there we go. And more Bakamud simulation component. There. Right? Okay. Then, what do we need? Let's go back to our Lua example. So we're talking about systems here. Populating this entity map is going to be something we're going to need to do. So the register system function maybe we can implement that. So, but now that we have this map here that tells us which components are owned by that entity, that means we can have collections for each of the component types. And then we're going to have to manage the indices into, say, their vectors for each of the components. Yeah. Right? Right, we've got Bring our little illustration skills back into play here. We got our 2 arrays. And we have position array, POS, our velocity component array, or vector, maybe array. We have arrays in Haskell, we can do that. Right, so the indices into these things. Right, we could make the entity ID. This is, I think, what the blog post was talking about. We could make the entity ID the index into these arrays, right? So, like, say our entity ID is 0, right? So we know exactly where to look up in the component arrays for a position component, the velocity component, for this entity, right? Well, then if this entity gets like destroyed or removed, maybe it's a player entity for their avatar and they get disconnected, right? We're removing it from the in-memory map, so the index is going to go bounds. We have to like do something with that, right? We could like, and I think their solution was they had another mapping that mapped the indices into these arrays and then managed some bouncing around, if I'm not mistaken. So 2 maps, okay. A map from entity to index and a map from index to entity. And a size. Right, okay. Right. So we then add a component with value A to entity 0. Entity 0 maps to index 0, and index 0 maps to entity 0. 1 to 1. Then add a component with value B to entity 1. Entity 1 maps to index 1, and index 1 maps to entity 1. Then add a component value C to entity 2. Okay, so I think I understand that part of their system. Alright, so they keep it packed, they move the last element D into the spot occupied by B and update the maps. So then we change what everything maps to. And then delete the value D from entity 3, moving the last element C into the spot occupied by D. Alright, so you know what the last element is if you have the size. So a vector. Okay, and they just wrap this all up into a class and all that stuff. And then implement a component manager, which starts taking a long time. I don't know if we need to get quite sophisticated with this. I don't expect us to be dynamically adding and removing components, but maybe we should consider it. But I'm not anticipating it, at least. Okay, so the system iterates on a list of entities with certain signature components, right? So like what we're saying here with register system, any entity that has a position and velocity component associated to it. Okay. What are we doing for time? We're running a little out of time. Okay. We got about 10 more minutes to go through this. So a system is any functionality that so it needs a list of entities, and we want some logic outside the system in the form of a manager to maintain that list. System has only standard set of entities. So they're leveraging C++ inheritance and stuff like that. We're going to do things a little bit differently in ours, but this is the general gist of it, I guess. We iterate through the entities. So our system is going to be iterating through those, like the Haskell server is going to iterate through those entities, right? And it's going to have registered systems to call, right? That's going to do all this stuff. Right, and so when we go through those registered systems, right, we're going to look through each of those for each of those registered systems. Okay, we got the physics one to do. We've got this system to do. We got the do damage system to do. We know what we need to look for. So as we're iterating through all the entities, right, we're gonna, if we stop on one that has the right signature for each of those registered systems, we'll pull those ones out and call the code for it, the system for it, which will do this thing. We get back the modified components, and then we update the components in the in-memory map for those components for that entity. So yeah, we'll need that map in the server state we have set up to be able to find out which entities and where. Yeah, to get that going. Where did I go? State over here. Yeah. Right. So, it's looking good, but I don't think we are going to have time to dig too much more in the implementation here. So I'm going to call it here for tonight. Thanks for watching the stream and hanging out. We've got a bit of a hashing out the design for our entity component system. Looks like we're on a path. Hopefully it's a pretty decent one. So next week, we'll get to implementing a little bit more. We'll get to implementing register probably, and being able to actually call these systems on our code. And we might have to do a little bit of map manipulation stuff, because we also need to load the components in as well that are live. So we'll do that as well, that sort of stuff. So yeah, I do these streams once a week, usually on Tuesday evenings at about 10 after 8 in the Eastern time zone. So if you like what you see, and you're on Twitch, you can follow me here and get up notifications if you have your notifications enabled, and you get notified when I go online. Otherwise, just write that down, show up next week, and I'll see you then. If you're watching on YouTube, you know what to do there. You need to like and subscribe and add a comment and all that sort of stuff. And my name's Agent Ultra. I'm on Mastodon on the types.pl server. So if you want to follow me there as well, you'll get updates about the stream and all that good stuff. Let's see what else. Go to the link above my head. It is declarative.tv. Website tracks a bunch of other streamers doing things in declarative programming languages. Some of them are like Haskell, but others like Elixir, Erlang, and so forth. Looking for audiences, looking for new people to hang out with. There's also a link to a Discord server on that site where we have a channel for this stream. So if there's a question you would like to ask, or that you didn't get to ask on the stream because you weren't here, you're watching on YouTube, the VODs, or you just want to hang out, talk about the projects, your project, this project, whatever, join the stream, join the server, chat with us, and hang out. And otherwise, check out agentultra.com. It's got my links to all my other stuff, like my GitHub, where all the code for this project lives. And you can find it there. So hopefully we'll see you next week. May all your monads be free and your types always check. And happy hacking out there.